Now let's see the case 2 of the sufficient condition, where I reconsider the equation which I have obtained from equation 5 of the previous continued theorem. So reconsidering equation 5, I have this already from the previous session. That implies I get my alpha as C1A2 minus C2A1 by A1B2 minus A2B1 is what I get as this new function when I bring this to the right. Next, now since alpha is the root of a1x squared plus b1x plus c1 equal to 0, therefore I have this satisfying the equation as a1 alpha squared plus b1 alpha plus c1 equal to 0, since alpha is the root of the given quadratic equation. Now with this being the root of, I substitute the value of alpha which I have here in this equation, so that I get a1 times alpha, which is c1a2 minus c2a1 whole square by a1b2 minus a2b1 whole square plus b1 times of alpha, which is c1a2 minus c2a1 by a1b2 minus a2b1 plus c1 equals 0, because this value is substituted in this equation. Now from the sufficient condition, I have this c1a2 minus c2a1 whole square with its own formula. So from sufficient condition, I have c1a2 minus c2a1 whole square is nothing but a1b2 minus a2b1 into b1c2 minus b2c1 by denominator, which is a1b2 minus a2b1 whole square, where this of whole is substituted with this from the sufficient condition. Then next, this is written as it is c1a2 minus c2a1 by a1b2 minus a2b1 plus c1 equals 0. Now we see that one of the common factor is cancelled from both numerator and denominator. So proceeding, I get this to be a1 times b1c2 minus b2c1 by a1b2 minus a2b1, which is the simplified form of this after cancelling one of the common factor. Next, I get this b1 times c1a2 minus c2a1 by a1b2 minus a2b1 plus c1 equals 0. Now I want to simplify the entire expression on the left hand side by simply taking the LCM. So let's see what happens when I take the entire LCM. So my whole of the LCM is a1b2 minus a2b1, which on simplification gives a1 times b1c2 minus b2c1 plus b1 times c1a2 minus c2a1 plus c1 times a1b2 minus a2b1 equals 0, because we have this entirely taken in the LCM, where the LCM is a1b2 minus a2b1. Now when I expand this, each of the term through the brackets, the expansion of brackets give me a1 b1 c2 minus a1 b2 c1 plus, arranging in the form ABC, a2 b1 c1, and this becomes minus a1 b1 c2, then this in the form a1 b2 c1 minus a2 b1 c1 whole of a1 b2 minus a2 b1 equals 0 is what we get. Now, when I see this, a1 b1 c2 and a1 b1 c2 are similar, so they get cancelled. Similarly, a1 b2 c1 and a1 b2 c1 plus and minus get cancelled, and a2 b1 c1 and a2 b1 c1 get cancelled, so that I get this to be equated to, I get this entirely equated to 0, identically equal to 0. That means what we have got is the correct root cut. So from here I can make it that when I substitute, alpha will be the root, because if I assume that alpha is the root of the quadratic expression, then I get identically 0 equal to 0. That implies alpha satisfies the quadratic equation a1x squared plus b1x plus c1 equal to 0. That implies alpha is the root of this quadratic expression. So this is how we prove that alpha is the root of the given quadratic equation. Similarly, proceeding in the similar manner, I can prove that alpha is also the root of the other quadratic equation, which is a2x squared plus b2x plus c2 equal to 0. And then finally, alpha is the common root. So similarly, we have alpha satisfies the quadratic equation, the other quadratic equation, a2x squared plus b2x plus c2 equal to 0. Therefore, since alpha satisfies, or alpha is the root of both the quadratic equations, therefore we say that alpha is the common root of the two quadratic equations. Which proves the sufficient condition of the theorem. Assuming on the given condition, we have proved in the sufficient part that alpha is the common root. This is how we understand the theorem, both through the necessary and sufficient condition. So let's see some special cases of the quadratic equations. So we have seen the general quadratic equation, which is in the form this. This is called the general quadratic equation. Now, there are three different cases which I'm going to consider here in the special cases. One is if I reduce the given quadratic equation in the form this, that is when b is 0. And secondly, I take the second case where my first and second is same, is what I take in the second case. So let's take the three special cases for the general quadratic equation ax squared plus bx plus c equal to 0, where my first case is taken in the consideration of ax squared plus c equal to 0, and my second case is ax squared plus bx plus a equal to 0, where this and this are same. And thirdly, I take a greater than 0. Then let's see what each of the three special cases conclude in their own understanding. Now coming to the initial case, clearly here I identify that b is 0, and of course my a is not equal to 0 is how we understand this. So in this case, my sum of roots, if my roots are alpha and beta, we all know the general representation of roots is alpha and beta, then we know that sum of roots is negative times coefficient of x, which is not existing here, by a, which is 0, and product of roots is c by a, is what we get. Therefore, whenever I have the quadratic equation in the form ax square plus c equal to 0, or a quadratic equation doesn't have an x term, then the roots of this will differ by same, because alpha plus beta equal to 0 implies beta is minus alpha. The roots differ by a sign. So the roots differ by a sign, but the values are always same. So beta is always minus alpha for these kinds of quadratic equations. Similarly, when I take the special case, the case 2 of considering the quadratic expression or equation, in this case I have taken the first and last is same. So assuming that a is not equal to 0, then in this case my sum of roots alpha plus beta is minus b by a, and product of roots is c by a, that is a by a, because my c is a. In this case my c is nothing but equal to a, therefore I get this to be 1. So this concludes that when a quadratic equation is in the form of ax square plus bx plus c, where the first and last terms are same in their value, then I have beta is 1 by alpha. That means the roots are reciprocal of each other. The roots are reciprocal of each other is how we understand the second case of the quadratic equation. Thirdly, let's consider the third quadratic equation, which is in its general form ax square plus bx plus c. Now in this case I have taken the special case of a being positive. So if a is greater than 0, that is if a is positive, that implies my sum of roots is given by minus b by a, and the product is given by c by a, and of course a not equal to 0 is how we take into consideration. Now in this case we will have an interesting case which arises where we compare between the quadratic expression and the value of a. So how we are going to do that is what we are going to discuss in the third case. So from this, if I assume that a is greater than 0, let me take the product of the roots, which is c by a. Now here I clearly identify that the product of roots, if it is positive, if I take the first case, if product of roots is negative, then if I take the product of roots is negative, then a being positive, obviously c must be negative. So we derive the sign of c based on the nature of the product of roots. Therefore, if product of roots is negative, that implies c must be negative, since a is positive, is how we conclude in this. Similarly, if my product of roots is positive, then in this case, then let's see what happens. If the product of roots is positive and a is greater than 0 is the case I have taken, then c must also be positive, is how we compare the sign, we measure the sign of c based on the sign of a and the product sign. So if product of roots is positive, that implies c must be positive, since a is positive or a is greater than 0. Therefore, c must be positive since a is greater than 0, is how we understand the case 3. So therefore, the product of roots define the sign of a and c. That is, if a and c are positive, then the product of roots is positive. If a and c are of opposite signs, one being plus and one being minus, either way, then the product of roots will be negative, is how we conclude connecting the values of the signs of a and c with the product of the roots, because alpha beta is c over a is how we conclude the sign change. So with these three different cases, we understand that as the quadratic equation changes, the properties or the roots will try to behave in a different way. In the first case, the roots differ by a sign. In the second case, the roots are reciprocal of each other. In the third case, the product of roots define the sign of a and c. This is how we study the different natures of roots, which we going to discuss here. But the most important note here is that if one of the root is real, the other root also must be real. It is not that one root can be real and the other root can be unreal, but the possibility is that only both the roots must be real. Therefore, if you get one of the root as real, then obviously the other root also must be a real value, but not an imaginary or a complex value. Now let's take the standard quadratic equation, which is given by f of x equals ax squared plus bx plus c equal to 0. Now if I say the roots of this quadratic equation are alpha and beta, then I'll derive some interesting properties from this general quadratic equation with its roots alpha and beta. Now let me start with the first formula, where if I say my c is not equal to 0 and of course a not equal to 0 and alpha beta are non-zero roots, then in that case, if I take the function f of 1 by x, for the given function f of x, if I take the function f of 1 by x, will have the roots 1 by alpha and 1 by beta. This kind of a function will directly have the roots 1 by alpha and 1 by beta. Is how we understand this property. Similarly, if I have, say, f of x minus k, if I consider f of x minus k equal to 0, then this function will have the roots alpha plus k and beta plus k directly. So we have a formula which says that if I subtract k from the function x value, then the whole quadratic function changes, and immediately that new quadratic function will have the roots alpha plus k, beta plus k is the direct property we identify here. Thirdly, we identify if I change the sign as minus x, then the roots of this function will be minus alpha and minus beta, because the roots will also change with sign as the value of x changes with sign inside f. That is, f of minus x equal to 0 will have the roots minus alpha and minus beta. Next, if I take k not equal to 0, then in this case my f of, if I divide with k, then I have the new roots which we are going to identify here. So when I divide k to x, then the roots of this kind of a function will be in the form k alpha and k beta are the roots which we identify. So this is how we identify each of the properties, the 4 different formulae connected with the respective functions as the roots respectively out here. We take them as formulae and then we derive for various problems which consider each of these cases, the special formulae connecting the quadratic equation and its roots. So let's see one of the theorem which connects the change in signs or is included with sign of quadratic expressions. So the theorem states that if there are 3 constants a, b, c belong to real number, there are 3 real constants a, b, c, and a is not equal to 0, then I have to prove that then the expression, then ax squared plus bx plus c equal to 0, that is the quadratic equation ax squared plus bx plus c equal to 0, has non-real complex roots if and only if the expression ax squared plus bx plus c and a, that is the coefficient of x squared, have same sign for all x belonging to real numbers. So this is the statement through which I'm going to prove. So let's initially start with the statement of the theorem, understanding the statement of the theorem. So it's given that a, b, c are real coefficients and a is a non-zero real number. Then I have to prove that the quadratic equation ax squared plus bx plus c equal to 0 has non-real complex roots only under the condition that they have same sign. That is, if this expression and a have the same sign for all real numbers of x, then the roots of this are directly non-real complex roots. Or if the roots are non-real complex, and then immediately I can say this and this have same sign. This is both the necessary and the sufficient condition. So initially I prove, assuming that this has non-real complex roots, I prove that the expression this and this have same sign, and conversely I assume that the expression and a have same sign. I prove that the quadratic equation has non-real complex roots. So let's start with the first assumption. Now before we start with, it is given clearly that let a, b, c belong to 0 and a, b a non-zero real number. Now let ax squared plus bx plus c equal to 0, the quadratic expression, have non-real complex roots. Now we know that when the roots are complex, the discriminant is less than 0. So using the property from nature of roots, this has complex roots implies delta, which is b squared minus 4ac, is less than 0, is how we get from nature of roots. So this implies when b squared minus 4ac is less than 0, 4ac minus b squared is greater than 0, is what we take here. Now we utilize this in the later part of the proof, where I take this as equation 1. So through this equation 1, let's see how we can show that this and this have same sign. So to do that, initially I consider the quadratic expression ax squared plus bx plus c. So the quadratic expression ax squared plus bx plus c, which I considered, I take a common out here. So what happens when I take a common from this entire expression is that when I take a out, this comes as x squared plus b over ax with this. So when a is taken out, the remaining two terms have this in this form. So I am going to make this a perfect square by using the complete square form. So for that, what I do is I multiply this with a times of x squared, which stands as a squared, plus 2 times of b by 2a of x, because I need a squared plus 2ab, which is 2ab. Then b squared is missing because we need to make this a perfect square by using b squared. Now since b squared term is missing, I add and subtract b squared. The b term, which is b by 2a whole square minus b by 2a whole square plus c over a, is what I get, such that this entirely can be reduced to the perfect square using a plus b whole square. So to continue with how, we can just expand this with the formula. Now let's try to expand with the formula. Now this becomes a times of a plus b whole square, that is x plus b by 2a whole square, and this on simplification gives me 4a square is the LCM, and therefore this reduces to minus b square plus 4ac is what I get. So this is what I get when I expand with formula. Now let me take this a to the left so that this comes out as by a, and this is nothing but x plus b by 2a whole square plus 4ac minus b square by 4a square, which I take as equation 2. Now as I see here, interestingly, I see that this is a square, and we know that all squares are positive, so this will be a positive term because all squares are positive, and 4ac minus b square is positive from equation 1 which we have taken. So this is positive, and this again is all squares which is positive, this from equation 1, and this is because all squares are positive, and here this also is a square, so any square term will be a positive term. So positive, positive, and positive when added gives me a positive term. Therefore I see that implies ax square plus bx plus c by a is a positive term, since each term of right hand side is positive. That is, each term of right hand side of equation 2 is positive. Therefore this entirely is positive, and therefore indirectly this term is positive, this being positive and this being equal to this. Now this being positive implies that the possibility of this fraction being a positive number is that they should be of same sign, because if one of them is plus and one of them is minus, then the fraction becomes a negative value. Therefore the rule says that if a by b is positive, implies a and b are of same sign. They should be either both positive or they should be both negative, but they cannot have opposite signs. Opposite signs make this negative. So therefore when a by b is positive, that implies a and b are of same signs, is the property which we have identified in the general properties of fractions. Therefore this by this being positive implies that a and b are of same signs, that is, this and this are of same signs. Ax square plus bx plus c and a are of same signs for all x belonging to R. So this proves the necessary condition of the theorem, where I assumed that the roots are complex, and I have proved that this and this have same signs. Now in my converse of the theorem, I assume that the expression and a are of same sign, and I prove that the given quadratic equation has the complex roots. So let's see how we can prove out the converse of the given theorem. So conversely, I consider that ax square plus bx plus c and a have same sign is what I consider for all x belonging to real numbers. Now using this, I had to prove that the roots of this quadratic equation are complex, non-zero complex numbers. Now since the expressions this and this have same sign, using the previous property, the fractional representation of this by this will always be greater than 0 for all x belonging to R, because when the two expressions are of same sign, their fractional representation will be greater than 0, cannot be of opposite signs. Therefore this must be greater than 0. Now, as we know that this has already been simplified from equation 2 as x plus b by 2a whole square plus 4ac minus b square by 4a square, which is greater than 0. This is purely obtained from equation 2, which we have already derived in its perfect square form. So therefore, substituting this for this from equation 2, I get this equal to the entire term greater than 0 from equation 2. Now, if I see this, I observe that this all squares are positive, so this is positive, this must be positive, and this obviously must be positive because this is positive. When the whole expression is positive and each of these two are positive, then obviously this must be positive. Therefore, when I take this term, I get that now since the whole expression is positive, that implies 4ac minus b square is positive is what we get. Since each of the term is positive and the whole expression is positive, therefore one term which is particularly here also must be positive is what we get here, which gives me the conclusion that if 4ac minus b squared is greater than 0, then b squared minus 4ac is less than 0 when I interchange this with this. That is nothing but delta, which is less than 0 because b squared minus 4ac is referred as discriminant delta. Now, when we connect with the nature of roots, when delta is less than 0, we assume that implies the roots of the quadratic equation ax square plus bx plus c equal to 0 are non-zero complex roots, which proves the sufficient condition. Therefore, the necessary or the theorem with its necessary and sufficient condition has been proved respectively for the assumption of the given quadratic equation having complex roots and proving that this and this have same sign, and then assuming that this and this have same sign, we have proved that the roots of the given quadratic equation are non-zero complex roots, is how we understand the theorem with both its necessary and sufficient condition. Now let's take the extension of the previous theorem which we have discussed connecting with change of signs. Now here the extension is with reconsideration of equation 2 which we have obtained in the previous case as ax squared plus bx plus c by a was derived to be x plus b by 2a whole square by 4a square is what we have obtained. Now, in this case, if I assume that if the roots of ax squared plus bx plus c equal to 0 are real and equal, equal being the condition, then we obtain that when the roots are real and equal, then we have delta, which is b squared minus 4ac, is equal to 0. We all know this by nature of roots. If the roots are real and equal, then delta, which is this, is equal to 0. So let's see what happens in the case of the roots being real and equal when substituted into this. So therefore, I obtain ax squared plus bx plus c by a is x plus b by 2a whole square, because the whole of this gets vanished when I substitute b squared minus 4ac equal to 0. 0 by 4a squared becomes 0, and hence we get only this. Now, that implies the expressions this and this will have same sign if this entirely is positive, but this is positive only when x is not equal to minus b by 2a, will have same sign if x plus b by 2a is not equal to 0. Because if this is 0, the whole of this becomes 0, and then it is difficult to predict the signs of the numerator and the denominator. So for this to be strictly greater than 0, this has to be not equal to 0. That is, x is not equal to minus b by 2a. Therefore, I understand here in the extension of the theorem that the given quadratic equation will have, if the quadratic equation has real and equal roots, then this and this will have same sign if x is not equal to minus b by 2a. This is strictly the condition when the roots are real and equal, is how we extend the theorem to understand the further properties of roots being real and equal.